Hi, I'm Thomas. In this lab, I recorded a roll of tape moving in a straight line at a roughly constant speed, analyzed the motion in tracker, built a glow script model using the momentum principle with zero net force assumed, and compared the model to the observational data. The goal of this experiment is to test whether a constant net force of zero predicts the tape's motion. If the roll of tape moves at a constant speed without changing any direction, then acceleration is approximately zero. But if it slows down or dramatically increases speed, there's some external force adding energy to the system. By Newton's second law, this means that the net force would be approximately zero, so the model should produce a straight line position versus time graph. I filmed a roll of tape moving across the screen in one dimension. The camera stayed still, and the tape moved left to right across the screen. I included a known length object in the scene to calibrate distance in tracker. And here you can see the tracker data. In tracker, I calibrated the scale using which is the purple lines you can see. Set an x-axis along the tape's path and track the roll's position frame by frame. From that, tracker produced the data table of the x position. And yes, I tried to track the center of the roll of tape to stay consistent. The blue line you can see is the calibration stick. In GlowScript, I modeled the tape as a particle moving in one dimension. I used the momentum principle. The change in momentum equals the net force times the time step. I set the net force to zero, so momentum and velocity remains constant, which leaves you with the simple thing that initial velocity is equal to final velocity if F net is equal to zero. This is my code on the right that I used to calculate it, and I gathered that data and put it into a predicted versus actual data graph using overlaying the observed x position that I gathered from tracker with the predicted x position from the glow script model. Both of these curves, as you can see, are approximately linear, which supports the constant velocity motion. However, the model line is slightly above the measured data, meaning that the chosen initial velocity in the model is either a bit larger than the tape's measured average speed, or the tracker measurement slightly underestimates distance. But overall, the model captures the trend well, linear x versus t with a smaller slope. There are some required questions for this lab. Firstly, what would happen if the positive x and negative x, if the positive x direction was swapped with the negative x direction? If you flip this x-axis in tracker so that the positive and negative were interchanged, every x value would change sign. Along with that, the velocity would also change sign because the slope of x over t would be negative instead of positive. The speed, however, meaning the magnitude of the velocity, would stay the same as it is directionless, and so changing the direction of the axis would not matter. The graph would look then like a mirror image across the horizontal axis. The second required question, which is why are we assuming F net equals zero, is because if you're rolling a roll of tape across a table, the normal force is going to be equal to the gravity, so it's going to stay motionless. And for this, we are assuming that air resistance and friction are negligible, which, given that in the real world they're not, that could contribute to why the actual data was had a lower slope and kind of trended off, as opposed to the predicted data using just the initial velocity. In conclusion, the roll of tape moved approximately at constant velocity, and a zero net force model based on the momentum principle predicted a linear x versus t relationship that matched the observed trend. Small differences are likely due to measurement uncertainty, friction changes, or the initial velocity choice, but with improved calibration and tracking, this agreement would be even better.